science. It's a trash science video. So anyway, carry my carpet music. Yay. Anyway, there's a link on the regular website. I did fix this little thing that does the whatever, so now you can get all the MP3 links off of a page. It's kind of convenient. But anyway, that's another subject for another day. I plan on doing with these toolbars for this website, so I gotta get around to that. Of course, it'll just make it nice and uglier for people to complain about, but whatever. You know. Look at that, it loaded one. You know, I don't have Grease Monkey loaded. Strange. Yeah, I don't know where that came from. Surprising. I must have had it, I have an old version of it loaded there. Anyway, doesn't really matter. What do I want to get to? Oh yes, okay, speaking of. So somebody posted a link on here, and to this silly thing. First ever photograph of light as a particle and a wave. It's just so annoying. You know, obviously you can't photograph light. It's a silly idea. And the interaction between light and electrons, you know, is complete. There's no evidence that it's an incomplete reaction. Absorption, readmission kind of a thing. So anyway, it's, you know, the link is just to a, I mean, I'll open it, but it's not a link to an actual article. It's a link to a YouTube page. You know, Google Plus page. It doesn't say anything. It just has, you know, fancy pictures, but, you know, obviously fancy pictures don't mean much. Don't mean anything really. So I don't, you know, again, I'm still working on this stuff. It's the overview thing. You know, the more you fiddle with this stuff, the more you just know something's wrong. You know, with the current perception of reality. Because, yeah, you start playing with these lasers, you start realizing they have a lot of nuance to them, a lot of strange properties. So I want to start messing with a magnet or, you know, electric fields and see if it changes the behavior of the laser any. Because it does seem like, you know, I was messing with different, you know, slit configurations, and I made this little racket here. You know, where it's got a piece of paper stuck in between the, you know, it's the slit. It's another, you know, it's this, well, whatever. Just to see, because it's kind of a curious fact about how light interacts with, you know, along planes, and also impediments, you know, objects, how it goes around them. You know, it's kind of curious. So I've been messing with that and trying to find focal lengths and, you know, how it, you know, how much of the light it seems goes around the object in terms of the diffraction idea. So it's all been very curious. But what I noticed with the laser, with that, is, you know, it has a shape, the beam, and you end up with a, it almost looks like a diffraction pattern, you know, and it's, but it's not. It's the shape of this beam, because as I rotated it, it wouldn't matter. And then when I rotated the slits horizontally, the beam was still going vertically, which was sort of interesting. The diffraction was going horizontal, but the beam itself, the, you know, that had kind of a pattern to it, was staying horizontal, which is just very, very curious. And no matter what I did, I couldn't make that beam, that shape, change. So you know, effectively, and it had a real, you know, it had a shape to it, like these, you know, like the little, you know, turn this light on, you know, you know, it had some definitely maxima kind of look to it, and, you know, but no matter, like I said, I turn the slits this way or this way, and I'd always end up with this being, you know, parallel to gravity, which, you know, is quite interesting. So I'd end up with a little bit of diffraction going this way when it was horizontal, and you know, I'd end up with weird diffractions off the side, you know, when it was, the slits were the other way. So anyway, just indicating that something strange is going on, from my perspective, because no matter how I turn the laser, no matter how I turn thing it's going through, I was always getting a horizontal shape to the light. Anyway, so it just seems to me, it indicates that somehow, it seems, you know, I mean, I have to play with it straight up maybe and see if it's radically different. You can almost see it there, you know, if I put it on that wall over there. I don't know if you can, well, you probably can't see that, it's on the wall. I'll put it in the darker spot. Yeah, well, you can't really see it there, but it doesn't, it definitely has a length to it. You see, if I turn the, so that's a 90-degree turn, and it still has the same exact length to it. I mean, you know, how can I be turning and it has the same length? I mean, frankly, that just doesn't make much sense to me. How can I turn? I'm rotating the. I know you can't see that, but I mean, you know, I'm rotating it. And maybe if I take the lens off, you can see that better. Wow, you can almost see. Oh, that's weird. I don't see. You know, when I'm looking in the screen, I can see a clear flare, you know, going in this direction, and I don't see that visually at all. So, you know, there's just so much of this light thing that's very, very curious. So anyway, it's going to require more experimentation and such, but there's something going. I mean, light is really, you know, I mean, you run it through the hair and it does all kinds of diffracting and all kinds of, you know, it moves all over the place. And, you know, the fact that people would conclude, you know, this wave thing is just such a, seems like such a, you know, they jumped on it too soon. Like it's some, you know, especially when you have so much evidence that light moves from point A to point B in a straight line. You know, all the evidence points to that fact. You know, unless it interfered, it's interfered with, something interferes with it. The other thing that's curious, you know, when you think of the two-slit experiment, it's just this idea of, you know, the idea is if this was the wavelength in terms of the distance between what I would argue are the photons. So I'm arguing that a photon of light is actually two photons that combined create a frequency. Oh, jeez. How about finding something that writes? We'll use this big heavy marker. It smells a little like fun. Anyway, so a photon is basically two photons because this creates the frequency, the wavelength is the creation of the beginning, you know, two points, two impacts. But anyway, so that distance, you know, in nanometers, would be the distance you would want to be less than for these slits. So it's a very, you know, it's a very narrow slit, and then the impediment in the middle, and the slits, the openings themselves, would be something maybe a little bigger than that, but not much. And so you're talking about something that's, you know, it's very compact. But anyway, the point would be, I would argue, is that this whole wave idea is that this light comes in somehow, and that it does what traditional mechanical waves and mediums do, which is it encounters a impediment and it creates a friction point, and then you have those bulges. But the funny thing is, the wavelength, since these slits are so small, the wavelength would essentially, you know, they would interfere with each other really quickly, because the first wavelength would be the diameter of the slit material itself. You know, this distance here, you know, the distance of the wavelength is the same as this distance across. So the first wave is essentially already in the other wave's space, which is kind of curious. And again, you know, the thing that lacks all of the idea of a wave interference pattern is a wave interference pattern actually doesn't create maxima in the sense that there's a double high and a double high, you know, times two, and a low that's times two. That's what you're getting here, you know. So there's a peak and then a super trough, and then a super peak, and then a super trough, and a super peak in this middle. So depending on the focus, depending on how far this distance is, you're either super low or super high. And that's sort of not accounted for in any real way in a description of what really happens in terms of the neutral spaces. So the neutrals, so you have these, the maxima are really just maximum range, from the super low to the super high, which ends up being a 4 times kind of thing. And what are called the destructive interference is just a neutral, where absolutely nothing happens. So again, I just don't know how you convert that into a light mechanism. But the point is this is just pretty much a pretty standard kind of mathematical formula. It's not a complex mathematical consequence of the wavelength. And again, most of these two-slit experiments, as you've seen them done, it's very difficult for them to come up with a method, that would, when you're doing this experiment, to have the slits, and then to be able to block one of the slits and have exactly the same light source, while you block the slit. So, it gets a little complicated to do that, because anything mechanical you put in here is going to change, obviously, can change the potential for some sort of disruption. But it seems like somebody should have done it by now in some sort of, way where they could just, close one of these slits in some sort of benign way where everything else in the experiment stays exactly the same. Just to be sure that these never nothing hits places change, because that's really the argument here, is that when you open this other slit, the theory is that somehow places where the light was going now become places where there is no light. So somehow the light that was hitting here, for example, now this becomes a nothing space. But again, the argument can be made that these slits are so close to each other, that any, you have to account for the fact that there's the light is hitting these surfaces, the extra light, and that could be creating the noise. This little tiny impediment, once it disappears as a tiny impediment, once it's no longer a little thing, it'll vibrate at a different frequency when this is made solid again. So it's kind of the idea that the thin impediment can vibrate at a higher frequency than the bigger solid slits. And so that could be changing how the light, as the photons go through, they'll interact quite differently when they're interacting with something vibrating more quickly, because this field that they're being diffracted by would be vibrating more quickly. It's logically coherent as an explanation. I don't know if it's correct, but I'm just saying it's something that has to be accounted for. Why is it not possible that middle impediment would vibrate at a different frequency than the more solid external sides? Why wouldn't that be your expectation? So anyway, obviously the frequency that something's vibrating at, like I said, is going to be key to where the light's going to get diffracted, and then what percentages at what angles. So anyway, the point is there's a lot of diffraction. Now the other thing that's curious is these, the putting a single impediment in front of a beam of light, and the fact that the light somehow goes, around the impediment and still creates a, a rather solid condition here, unless you get the focus just right. So if you bring the focus in, then you'll see this object, but as long as you're outside the range of the focus, once you're outside where then these lines can converge. And that's it clearly has the appearance, like I said, of the fact that there would be a density of static electricity, or whatever you want to call it, and particles, electrons, around objects, and that as the light goes through those electrons, that's what's deflecting the light in both directions, both in and some of it going out. So it's scattering the light out and bringing it into a focus. Now, a curious thing I noticed, fiddling with that, was that the image you got, let's say you put a solid impediment of, say, a certain size. As you made that impediment, and the light's going this way, you would get a view of it as almost, half of its size, in terms of, if you got a shadow, it would be reduced to like a half of its, what it was. Like there'd be a clear indentation, of the shape like this, in terms of the intensity of the light would be around this focus. So you'd have so if you had a little bit more light, you'd see the real size of it. But where the bright light was, you'd have this definite convergence. And there was a point where you would just, break it to nothing. So as you got thinner and thinner, there's a point where the middle, the impediment essentially disappears in terms of creating a shadow of any kind. So again, I don't know what that means. I don't know if it means anything. It's just curious, and it's just curious that all this is, in my opinion, understudied. The underexplained. Because it's, I think different surfaces would have a different impact. This idea, the whole idea of getting something on its edge, because that's another thing that's curious about the light too, is that you can actually get the with those laser beams, if you get this thing bent just the right way, you'll get the light to show up on both sides, which is kind of curious, because you would think it really wouldn't be able to hit both sides, and leave a line of reflection on both sides. You'd just think there would be always some kind of defect or something that would create skipping. So it tends to make me think that there is something that tends to push the light into the surface, or migrate it that way. So anyway, something to work on. Something else to fiddle with. I mean, clearly, there's just clearly room here, with this wave idea of light. I mean, this is it. This is all they have to justify this wave idea, is the fact that light is affected by its interaction with certain surfaces. And the argument would be, just like Einstein's lensing, is this, it kind of affects this argument in a way, because is it really gravity that's moving the light? Is it the bent space? Or is it the nature of the space around gravitational bodies, and the fact that they would tend to have a lot of charged particles to diffract light? So you would expect a lensing just from the density of particles. Yeah. So a lot of places to go with this stuff. And these other experiments have the same sort of pattern, and it just doesn't appear wave-ish in these other circumstances, like the thickness of glass, and the fact that as you change the thickness of the glass, it changes the reflectivity, how much light is reflected back out of the glass. is changed based on the thickness of the glass. And there's nothing intuitively that says that's a wave phenomenon, in my opinion. It doesn't scream wave interference in any realistic way. You don't have this obvious circumstance where you have where you can duplicate a water wave to explain the Newton glass phenomenon. Yeah, so, but you have the same pattern in terms of a all or nothing. There's spaces where there's nothing, and spaces where there's 4 times, which would have been in terms of a 4 times displacement. That's the wrong way to put it, but the point is that whole idea of it being squared happens. And that this brings up the whole idea of the way that gravity works by nature. It has that inverse square rule, and maybe that has something to do with this too. The fact that half the distance is 4 times the effect. So I move my hand halfway. I move it half the distance, and it's 4 times bigger than it is here. In terms of its intensity. Wouldn't it intuitively mean, when you think that intuitively it should be, you go half the distance and it's twice as big, not 4 times as big. So, that's not a light phenomenon. We're not all screaming, well, the photons are doing that, because that effect is not a photon effect. It's an effect of the reality of the distance. You can measure it with a ruler. It's a real thing. It's not just an optical illusion. And certainly with gravity, it's not an optical illusion. It's gravity. But it's optical in the sense that, yes, by my argument, gravity is a photon without frequency. So, anyway, I really want to get back to the magnetism and electricity thing, because, that's where that's like the real, that's where you tie the small universe to the big universe. So I did see a Degrassi Tyson clip somebody had posted or whatever, and, from like his radio show. He's just so obnoxious. But anyway, somebody was just making the classical argument that, why aren't, since atoms have parts circulating around each other, why isn't it appropriate to visualize it as if it was a solar system, or like the universe, the big universe? And of course, the Degrassi Tyson guy was basically just saying, the two are, describing it as if the two have nothing to do with each other. And obviously I'm arguing that I think it's wrong to say nothing. They obviously have something to do with each other in the sense that it's the same force, it's the same mechanics. It's just quite obviously the scale is so much different. 100 to 1 versus trillion to 1. Those kind of scales do change the ball game. But let's just, for the sake of refreshing, the electron, let's say if it was a million photons, it's something like, whatever the numbers are, and you got the proton and the neutron are the key players in the nucleus, and that these are all bound by the fact that they're creating, that gravity goes through them in one form, non-polarized, let's say, and it comes out of them polarized, so either negative or positive. So it goes in one way, comes out another way, and that each of these bodies, depending on their positive or negative potential, are sensitive, are affected by positive or negative. And so if they're affected by positive, that means a positive goes in and a negative comes out, and vice versa, negative goes in, positive comes out. And that's creating what appears to be an attractive force, which is really just the absence of force. So if something creates something, you're vulnerable to positives, and they're throwing negatives at you. The negatives just go right through you without effect, and they come out positive. You still convert them, but they don't mean anything to you. And it's only the ones that are negative that you're going to be impacted by. So if they just keep throwing the kind that are invisible to you, then obviously the external pressure that's always banging into you is going to be greater, and that's going to create the illusion of an attractive force. But really, all the forces are pushes. So everything really gets pushed into each other, rather than anything being attracted to each other. So here in the nuclear thing, it's this force, and then when you got magnetism and electricity, it's really the same thing, but obviously now the scale's even bigger, and you have whole pieces of matter, that have that are producing, gravitons are going in, and they're producing, massive amounts of positive and negative based on the arrangement of atoms in certain configurations where the atom is a dipole, and so the atom, has a disposition, positive and negative. So when stuff comes in one way, it goes out negative, goes in negative, it comes out positive. And once you arrange atoms in that way, you'll create what is called a magnetic field. And then if you change that polarization by 90 degrees, you'll have electricity, the electric field. And the two would obviously be able to induce each other. Well, not obviously. I guess it's something that needs to be explained. But you can figure that there would be a half ratio kind of thing where that key 45 connection between the two, that at the 45 degree angle you're just as far from one as you are from the other, and the two are essentially connected at that 45, and so one becomes the other essentially at that specific angle. That's angle is a good enough way to put it. So it does get kind of complex though, because you say, well, magnets work no matter which way you turn them and all this kind of stuff, and that's true, but we also don't know how they would work if they were outside of a magnetic field, the magnetic field of the earth, the magnetic, there's magnetic fields like gravity extend forever essentially, theoretically, and so they're always going to orient a gyroscope. Let's say if I had a gyroscope and I tried to take it outside of any influence, I probably can't do that. There's probably always gravity somewhere that's the strongest, and it'll always find that gravity and align to it. So there's a fundamental reference for polarization. As you move things, the polarization will always realign to the pre-existing relative field. So if they're in the same relative field, and they kind of always are, you can't really take two magnets out of the relative same field, because they wouldn't be able to influence each other. As the distance increases, you're not going to be in the same relative field. So anyway, that's a whole nother subject. I just want to say there is more to get into on those two subjects. Electricity and magnetism, it's another big subject. But I guess I'm just kind of focused on this light thing just because I'm trying to get some sort of experiment to actually work. And so far it's been a little frustrating. So I have to work some more on it. I have to get a better light source. These lasers are strangely not a very consistent source. And I was thinking of doing it the classic way, where you shoot the laser through an aperture. The original two-slit experiment has that as a fundamental component of how it works, is that the light comes originally through one slit, a hole, a little aperture, and then it goes to the, two slits. So, it's getting a consistent, coherent light source, and then you need it to be of, monochromatic. You need it to be of the single frequency, or else you end up with the lines on top of each other. So, yeah, I'm just, maybe I should make a prism or buy some prisms or something and then try to use sunlight or something. I don't know. Just have to find a better source of a, I guess a halogen light might be interesting to try. And then just, split it into, some other colored light. Yellow or something. But anyway. So, I don't think there's much else to say. Yeah, so I'm just sort of stuck in working on it mode. But, and I've been watching lectures and doing all that kind of, I'm doing more research, background stuff. But the more you hear about what goes on in the world, it's just all these assumptions. Like it's all this, very sloppy science. I mean, to call this a photograph of light, it's just not technically correct. You can't photograph light. It's just wrong to say you're photographing it. It's just wrong. You're synthesizing something. And they've gotten so used to synthesizing things, they don't know the difference between real and make-believe. And it's very dangerous, I think, for physics to do that, and I think for any science to do that. To take their simulations and their synthetic constructions, until they've really, really hammered it out and so, really worked it hard to find out whether there's some other explanation. And you see that a lot with the entanglement experiments and the eraser and all that stuff. They're experiments that rely on a lot of hardware, mirrors, all kinds of different things, and you're saying there's reason to believe those things break your experiment, that you can't do that, and say you're working with the same photon, but you're really not. Yeah, I mean, it gets complicated. Like, the fiber optic thing, I haven't done too much with that, just because it's hard to get enough light to go through it to do something seriously constructive. But, yeah, I mean, it's curious. But, I mean, you could argue when light goes through one of these light tubes, and it's reflecting. I mean, are they pure reflections? Is there any such thing as a pure reflection? And what, if light has any character at all, is any of that character being lost through those reflections? I guess I would argue that there must be, because I think even if you accounted for the more distance traveled based on the reflections, the light's still traveling much slower than it should be. I mean, the amount of distance isn't very much because the angle of incidence of the reflections has to be very sharp. So it's not like it can be going back and forth this way. It has to be going at a pretty sharp angle. So there shouldn't be much degrade in the speed of light as it travels through fiber optics. But I think there is a lot more than would be accounted for through just reflections. That, more than just the amount of time it would take to bounce off of things. So I think they are being absorbed and then readmitted. But that's just what I'm thinking. So anyway, this gets so complicated, and it's just these bits are incredibly tiny. And so, whenever you're doing this stuff, you're talking about billions and zillions of things, the discrete little packets of stuff. It's not like there's a stream that they're all, I've said it before, but when I'm looking at something, it seems like there's just a stream of photons coming off of something in some perfect straight line. And that's, I think we can know mechanically that's not possible. It's not what's happening. They're little bursts of photons coming from different electrons, very, in different positions that are always moving. So that the stuff the light's coming from is moving around, and we're just getting bits, little hunks of light, in different little packs. Maybe just 2 photons at a time, maybe 5, maybe 10, of the discrete gravitons, the discrete particles. And then there's another stream that comes from almost the same location, but it's not really the same location. It's just almost the same location. And our eye is just, we don't have the resolution. We don't have the visual resolution to be able to see the difference, because it's more than just microscopic. It's sub-microscopic in terms of the fact that it's coming from a different place. A very slight angle different, but it's a different place with a different, slightly different angle. Each stream of photons, each photon, has a subtly different distance that it traveled to get to your eye. Anyway, yeah, I'm just saying, it's hard to model something, so incredibly small, just as it's hard to draw a picture of the universe, and get an idea of the size, the amount of stuff in it. Because you really can't do it to scale. You can't put the stars in place in the right scale to the amount of space that actually exists. Since you can't make a model of the solar system, because then it's just orbits. You wouldn't even be able to see, the size differences if you made it to true scale. Just because the distances are so great. The big distances would just make the little distances look like no distance. So, yeah, but that's, physics is supposed to. I think it's just a huge mistake that physics keeps allowing itself to use models that aren't accurate. They're too convenient to perception. And it's like the Dr. Quantum video, or all the demonstration of the two-slit experiment, where they show a two-slit experiment where they just draw it, hugely disproportional to, the actual circumstance, which is essentially, a dot, a tiny space between the dots and another dot. This is the real experiment, and they always draw it, like this. So it's deceptive, because you get the idea that it's the single impediment experiment when you see it to its real scale. And it's only a two-slit experiment when you do this to the experiment, when you do this to its actuality, when it's really this. I think you know what I mean. Anyway, yeah. So, yeah, it's probably way, I just want to keep making videos. I probably shouldn't make this video because I really didn't have anything new or solid. But I do want to just keep making videos to just stay in the game. And, yeah. So, but yeah, I mean, I gotta find the catch. There's a catch here. There's a catch that, what I'm really going to work on is the water wave interference pattern, because it really is simple, and there's a reason why the pattern's there, just like there's a reason why half the distance 4 times the size. there's a reason, and understanding that reason, I think, will explain the two-slit experiment. I have to go back to the spin on electron one. You know, that's another one of these quantum things where they have the spin on the electron and it only spins up on, well, whatever. I have to go back to that one because I think that one leaves room for explanation also. So anyway, yeah, that's about it. Okay, so that's probably enough. So anyway, till the next time.